Assalamu alaikum warahmatullah. This is a video actually for tutorial 1 where this video will help you to solve things that I will post later on in the tutorial task. Okay. Uh, Consider this tutorial video as basically not more on having the problem solving, but on the basic introduction of Smith chart. What are the operations and what can we find? What are the capabilities of Smith chart and so on and so forth. These things we will learn in this tutorial. Later on, I will post some problems, and based on those problems, you need to solve those problems based on whatever we have learned today. So this is what Smith charts. You are already familiar with, as far as I know, that this is the complete Smith chart. So where basically there are some things that we use these things, these places to find some parameters, and we plot our given impedance here. Okay. Now I tell you one thing, that if there is a given impedance, this Smith chart actually deals with all the type of impedance related things. Okay, and impedance related means the admittance also, because admittance comes from impedance, and all the other things related to impedance. Okay, so but the byproduct can be many things, many thousands of things from the Smith chart, and it's actually a revolution when the Smith chart has been invented, and then it's made so easy for all the RF designers to design RF devices. However, this is a very basic one we will learn today. Not will go further, but in upcoming chapters or upcoming classes, this basic Smith chart introduction will help you a lot. It will massively benefit you. So now we go inside the content is, since we talk about the impedance, so we need an impedance, right? So let's say we have an impedance of Z is equal to X plus JY. Okay, so if this is an impedance, that we can plot this one here in this Smith chart. How? This is the real part, right? And this is imaginary, right? So we have two different axes where we can plot real and imaginary separately. Okay, and then when they intersect together, that will be the point of our this Z. Okay, now all the real parts will be on top of this one. Let's say the real part is 0.6 and the imaginary part is 0.3. Okay, so we find it here 0.6. This is 0.6, and then we find this is the real part, right? Now what about the imaginary part? Okay, imaginary parts are these are the arcs of imaginary. Okay, so these are the arcs of imaginary arcs. If it's a positive one here, then we plot it up. If it's a negative one, then we plot it at the bottom, which is actually, we call it this part, the positive part, we call it inductive. And this part we call capacitive, the bottom part. Okay, capacitive. Okay, so we were here that we located our real part, no matter is it inductive or capacitive. Okay, so our real part is here. Okay, so we got our real part. So remember one thing, that even though it's negative, you need to put it here. Okay, so this doesn't have any polarity, but it's positive or negative, it will determine here. Okay, now we already have 0.6, what we have located already. Now we need to find plus 0.3. So plus means up. Now we find here, see, 5, 4, 3. Okay, so this is our 0.3 point, right? And this is our circle of 0.6. So here, and then we come here. So this is our goal, to find this point. That's how actually we will plot our point. Okay, now from this one, if you try to find things, then you basically, I forgot to tell you that you need this pencil compass actually to draw circles here. Okay, you need a ruler, and of course you need a pencil for sure, and the eraser. So let me tell you one thing, that you have to calculate all the points from the origin, this point. Okay, so you take this, and then from here, okay, but first you have to do like this. You need to draw a circle, sorry, draw a radius which is coincide with this. Okay, so this is the length actually that will help us to figure out many different parameters. Okay, and then what we're gonna do is we're gonna draw a complete circle here. Okay, this is what we call actually SWR circle. Call it SWR circle. Okay, so our plotting is done, right? Now how to find parameters and what to find. Okay, and what to find. Let's say you want to find SWR, then you need to find this. Okay, and since we have already measured this much value, from here we have already know that this much. Okay, here, right? So we have this much, so we keep this one and we plot it here. So this is your value of SWR. So SWR is 1.9. Okay, and then the other things, let's say return loss you want to find, then you need to put it here, and then you find from here return loss. And then you have not this one, you don't, this is not your concern. This you need to find reflection coefficient. Similarly, you put it here, and then this will be your reflection coefficient. Here it is 0.31, and then like this you find all the other, like attenuation in dB, not this one, but this one, transmission coefficient. Okay, reflection loss in dB. Usually we don't find these things actually, but this we need to find, this we need to find, this we need to find, these things this we don't need, this is SWR return loss, these things we will find. However, it will look a little blur for you in the beginning. I will move on to another problem actually, and then I will try to solve it, and from there actually you will understand. However, before I move on to another part, okay, I want to tell you one more thing, that this is given, right? That you have Z is equal to, let's say this is load impedance, this is your load impedance ZL, and you have 0.6 plus j 0.3. Now from this you can directly, this is impedance, right? You can calculate your admittance. How? You just take this value, take the, sorry, you keep this, and in the circle you draw an intersect just opposite of this circle on that point. Now this point here, the value of this point will represent your y. If zl, then yl will be your yl will be your the admittance, isn't it? Let's find here now. Okay, we are here, so let's find the real part first. So this is the real part. Where we find 1.4. So we write down here 1.4 already. Now this is negative side, right? So this is negative, and then we will have this. So let us try to find as close as possible. This one. So here, so it's between 0.7 to point, so it's like 6 point something. It's like let's say 6.9, 6.7. So it's, sorry, 0.67, 0.67 j. So this is how you can find it. So if you find here your zl, you can find your yl here. So we move on to solve a problem first, and then of course you will understand how the things work. The problem here is this one. Okay, so the problem says that a load impedance of this, means this is ZL, terminates at 100 ohm transmission line, means this is Z0. Okay, and the line is this lambda long. You have to find the reflection coefficient of the load, the reflection coefficient of the input of the line, the input impedance, and the standing wave ratio, and the return loss. We'll find it the same way as we did. Now here we are, where this is ZL given, right? It's not the real part actually. You can give anything. Okay, so ZL is given as 40 plus J 70. Okay, so a person is standing here now. Okay, a person who is standing here, let's say somebody is standing here. So ZL is given. So to find the Z in, towards what we have to go? Towards the source, isn't it? But in Smith chart, we don't say it's towards the source. We call it towards the generator. How? With this length. You need to travel through this length, which is given here 0.3 lambda. Now, how you will find this length and where you will find that towards generator? So towards generator, okay? So we call it walking towards the generator. How? We go back to the Smith chart. Here, check here. there is a certain place where actually we can find. So here you can see that this is the point here. It says the wavelength towards the generator, means if you move clockwise, then you will find the generator, and if you move anti-clockwise, then you will find the load. Means if the Z in is given, then if you want to find the load, you need to go towards the load, and in this case the ZL is given, so we will go towards the generator. So we will follow the clockwise. So it's anti-clockwise means towards the load, and clockwise means towards the generator. You will understand when I solve the problem how to implement this tactic. Okay. Now come to the solution. Now that we are wondering now that as far as Smith chart concerned, there is no 40 or 70 or something like this, or 100, because these are mostly, you check here, 0.6, 0.4, 0.2, 1, 1.2. How can we do it? Now to do so, there is a technique that we have to apply, that we need to normalize it here. Normalize it what? The ZL normalize, you can call it ZNL also, LN also, that the given load impedance divided by the characteristic impedance, means Z0. So we divided it. When we divide it, so we get a value which is actually plotable on top of the Smith chart. So I take a fresh Smith chart and try to solve it. So I took a fresh Smith chart and I write down the value first. So the value of ZL given is 0.4 plus J 0.7. Actually not given, that we have calculated ZLN here from here. Okay. So this we will plot. Okay, so 0.4, we look at 0.4 first. So this is the 0.4 point, and then we look at 0.7, 0.7 for the imaginary part, which is positive. So it means this side. So we find this 0.7 here and this. So we try to go on. And we stop at 0.7. So this is our point. So you already found our ZL here. So this is ZL, okay? ZL normalize actually. And now the same thing what we're gonna do, we're gonna take this, take the value, and then we draw a line here until this point. Okay, and this will be our VSWR or SWR circle radius. So we take this and then we draw a circle here. Okay. So this is the length, that this is the memory that we will keep to find out our different parameters. Number one parameter, find the reflection coefficient at the load, means the load reflection coefficient. So whatever the related to ZL, we will find in this Smith chart. If we don't change anything with this value of ZL, this length, we'll find directly the reflection coefficient at the load here. So which one is the reflection coefficient? I said that you don't need to concern about this. Okay, you need to concern only this. Okay, so you take this one here and put this here. So this is your value, and which is actually basically 0.59. Okay, so our first gamma L, we got it 0.59. But what is the angle? Okay, angle you find here. So you need to extend this one, this line, and see these are the angle. Okay, so this is in between, this is one, this is around 105, I suppose. Remember one thing, that it may not be accurate, but it can be an approximation, which is very, very close approximation. So this is 100 and, let's say 105. So we put it here, 105 degree. So this is done. Our first one is done. Okay. Sorry, I think I made a mistake. This should be, okay, wait. Yeah, no, I'm right. I'm okay. So remember one thing, that you should find always the incremental value. Okay. So whatever it coincides with here, you will take it. Okay. Now, so this one is done, right? Okay. So our first value, find the reflection coefficient at the load, is done. Reflection coefficient at the load is done. Now the reflection coefficient at the input to the line, this is what we find. But we will find that this one later on. Okay. We'll find the standing wave ratio first. Okay. So standing wave ratio here, this is SWR line. Okay. So we put it here and try to find. So which is around 3 point something. SWR is 3 point, let's say 3.9. So our SWR is 3.9. Okay. So, and one more thing, what is return loss in dB? Let's say we find our return loss in dB. Same, we go here again. Return loss in dB here. So around 4 point. Return loss we calculate from here. Okay, so it's 4.7. Let me remind you that this will not be 100% accurate, but it will be very close. So return loss means RL is equal to 4.65 dB or you can write 4.7 dB. Okay, now what is left? Return loss is done, standing wave ratio is done, reflection coefficient at the load is done. So now we're going to find the reflection coefficient at the input line and the input impedance. Okay, to do so, actually we need to use the value of this, because it says that the line is actually 0.3 lambda long. Okay, so it means that from here we need to travel towards the generator to find our source or the generator, where we will find our input impedance and input reflection coefficient. So what we're going to do is, as I told you, that now you have to find towards the load or towards the generator, right? So we're going to go towards the generator. From where? Okay, from here. Okay, so this is the towards the generator, right? W, T, G. How much you will go? Okay, you go 0.3 lambda. Okay, now these are the lambda lines, right? From here, how much we are here? At this point, we have 1.105 lambda here. Here, 0.105 lambda. We are standing here. We are standing here. So if we add 0.3, so it means 0.405. So if you add 0.3 lambda, it results 0.405 lambda. So we try to find what is 0.405 lambda. So we move here, we're going on, we're going, still going here somewhere. So here we find, so 4 and 4, 0.4 and 0.41, in between this 0.405. So 1, 2 and a half. So this is the location of the generator or the input. Now same thing, what I'm going to do, I'm going to take this one and I'm going to draw one more circle. Okay, now here you need to find out that on this circle, okay, on this circle, which one is intersecting on this. So this will give us our anything related to input, either input impedance or input reflection coefficient of the line. However, one significant thing you have to notice here, that the radius has not been changed, isn't it? It means the reflection coefficient is not changed also. But what changed? Okay, the change actually happened here. Here. Okay. So it means that we need to find the angle only. So to find this in, we are here already, 0.59 can write, but what will be the angle? We find here. So the angle is minus 11 minus 11, let's say, sorry, 110 112. Can write minus 112. Or if you add with you need to subtract with sorry, add, I believe. Add with 90. Or no need to add anything, actually it will make it complex, sorry, because I don't want you to make it so complex. So do it like this, that whatever you get it here, okay, you put it here, because the up is actually towards the generator and the bottom is towards the load. So don't confuse on these two values, because when you go towards the generator, you take the up one, and the bottom one is this towards the load. So here it's minus 1 1, here is minus 1 1 2. So the result is minus 1 1 2 here. Okay, one more thing is the input impedance itself, isn't it? Okay, how to, now we know how we plotted here, right? That we go here and then we come from here and then we got this, right? The same we will do it in a reverse way. So here we find this one first, and then we find this, let's say this one, not to be exact, but to have an approximation, just okay here. So it's 3.8 or 3.9, this is 3.9, sorry, 0.39, and then this one is negative, you find it here, 6.2, sorry, 0.62. So the value of Z in is equal to 0.39, 0.39 minus, of course, because this is at the bottom, and if it's up then it's positive and its bottom is negative. So we have 0.0 J 0.62. So this is your answer. So we have all the answers now. So the reflection coefficient at the load is this. SWI is 3.9. The return loss is 4.65 or 4.7 in dB. Input reflection coefficient is same magnitude but in different in angle. And then the last thing is the Z in. Okay, so I hope that you understood the whole scenario. You need a lot of practice and a lot of conceptual, how can I say, understanding is the most important thing here. Okay, so focusing on this one, it will help you in the all the future things that we will learn, because in matching we need it, in other things, all the other maybe in LNAs we need these things. Okay, so I hope that you understood. If not, then I'm always here. I will try to help you as much as I can. So far this one, this all. Later on I will put up some problems related to this. Okay, and then you can solve it, and once you solve it, you can you can suggest to me, you can give it to me to check your problem, and if I see that is right, then I will try to upload my solution or the solution which one is the right one. So until then, I thank you for your patience. It's a kind of long video, but however, um, I don't uh, believe that you will learn everything. But so far as this is as much as I can give it to you. Uh, until I make another video, I'd like to excuse myself. Assalamu alaikum wa rahmatullah.